In this video, we'll look at trigonometric substitution. There's three cases that we'll focus on. The square root of a constant squared minus a variable squared. If we see this, we'll use a substitution, x equals a sine theta. Case 2, the square root of a constant squared plus a variable squared. Notice it has its own substitution. And case 3, the square root of a variable squared minus a constant squared. It has its own substitution to make. Notice in all three cases we don't see an x term in these quadratics. If we do see an x term, then we'll need to do an extra step using completing the square. We'll do an example of that in a different video. Up first we have case 1. It may not be obvious right away that this is case 1, so I'm going to show an extra step. This is the integral of x cubed divided by the square root. We'll replace 16 with 4 squared. Then we have minus x squared dx. Now it's a little more clear that the a term up here is 4. So we want to use x equals 4 sine theta. A sine theta is 4 sine theta in this case. Then the derivative dx is 4 cosine theta, d theta. We can now rewrite this expression making a substitution. Integral, replace x cubed with what we defined x to be. That is 4 sine theta cubed divided by the square root of, I'm going to rewrite that as 16. Then minus x, again we replace with 4 sine theta, and that is being squared. Then we replace dx with 4 cosine theta d theta. I like to put d theta on the outside. From here we'll simplify. 4 cubed times 4 is 4 to the 4th. Sine cubed theta cosine theta. All divided by the square root of 16 minus 16 sine squared theta, d theta. If we want, we can pull the 4 to the 4th outside the integral since it's just a constant. We'll be left with sine cubed theta cosine theta in the numerator. And in the denominator, we still have a radical. And the goal is to have a perfect square under the radical so that we can eventually remove the radical. It's going to take a few steps to get there. Let's start by factoring out 16. We'll be left with 1 minus sine squared theta. Just copy what we have in the numerator for now. And in the denominator, we'll keep the 16. 1 minus sine squared theta. Hopefully we recognize that as a trig identity. That is equal to cosine squared theta. Still under the radical. And d theta is still on the outside. 4 to the 4th integral sine cubed theta cosine theta, all divided by square root of 16 is 4, square root of cosine squared is cosine theta, d theta. Finally, we've removed the radical, and we can simplify a little bit more. We can cancel the cosines. 1 power of 4 we can get rid of. That means we're left with 4 cubed on the outside of the integral. 4 cubed integral of sine cubed theta d theta. As you can see, this is a long, tedious process. We've simplified a lot, but we still have to simplify a bit more. I'm running out of space, so I'm going to copy this up here. We have the integral of 4 cubed sine cubed theta d theta. Remember, when we have odd powers of sine and cosine, we can rewrite those integrals and use the Pythagorean identity to help us evaluate them. So here, 4 cubed, we want to pull out 1 power of sine theta. We'll be left with sine squared theta d theta. And the reason we do this is so that we can rewrite sine squared theta using the identity 1 minus cosine squared theta. Now we can make a u substitution. If we let u be cosine theta, du is negative sine theta d theta. Notice that negative sign does not occur in the integral, so we'll just divide by -1, making that negative du and positive sine theta. We now have 4 cubed integral of, now we're making our substitution, 1 minus u squared du, and we'll make the constant a negative. At this point, we can finally integrate. We have -4 cubed. Integral of 1 is u. Integral of u squared is 1/3 u cubed. And plus c. Let's go back in and replace what u is. We said that u was cosine theta. And now we're almost done. Notice we're in terms of theta though. The original problem is in terms of x. So we need to go back to our rule from earlier, the substitution we made. We said that x is 4 sine theta. We'll use a triangle to help us find those values now. Let's divide both sides by 4. We have x divided by 4 equals sine theta. Now we'll use one of those rules you probably heard in trig, SOHCAHTOA. We'll draw a triangle and an angle. Sine is opposite over hypotenuse. So opposite x, hypotenuse being 4. We need to know this side. We can use the Pythagorean theorem to find it. That unknown side is going to be the square root of the hypotenuse squared minus the side squared. Recognize that that quantity we've actually seen before. If we recognize that from the original expression, 16 minus x squared is under the radical, so that should look familiar. Most of the times that's going to happen. There may be some cases where this result is not what we started with, but most of the time it will be. Finally, we can rewrite this expression to get our final answer. We have -4 cubed cosine theta. Remember, cosine theta is adjacent over hypotenuse. So adjacent is the unknown part, which we just found. 16 minus x squared divided by the hypotenuse, 4, minus 1/3 times cosine cubed. Cosine, again, we found to be the square root of 16 minus x squared all over 4. and that is being cubed. And then, of course, we want plus c. So it's a long and tedious process, but we finally got the answer.